is Tamargo. Go!
Hello, everyone. Thank you to the organizers for allowing me to speak in this auditorium. And I want to tell you about this recent paper and some work in progress, which is the one-sentence summary is about how string dualities relate the different ways we have to construct QFTs in string theory. So in particular, the context is we want to build superconformal field theories in 5 dimensions. We know that 2 of the main tools that we have are M-theory geometric engineering, where we translate the geometrical properties of some Calabi-Yau threefold to the field theory, or webs of fibranes in type 2b, where you also understand properties of the field theory by moving branes around and so on. But we know that M-theory on a torus is the same as type 2b on an S1, so these 2 approaches should be related, and indeed, for example, if we restrict to the case where the geometry is toric, then all your data can be encoded in some simple combinatorics. This is called the toric diagram, and well, you obtain both the full geometry as well as a brainweb from the same data. Now, the point is that in the brainweb, you can add 7 branes while preserving supersymmetry, and you can start performing some manipulations with those. In particular, you can make Haney-Witten moves or trigger some Higgs-Franz flows, as Senga was saying. And you can go slightly beyond the normal toric diagram by adding some decoration, which is colloquially known as a white dot. And what we were trying to understand is what is this in the geometric engineering picture. So what we do is to think of in terms of the mirror to the toric geometry, because this has a very intimate relation with the brainweb. You can really see directly. And then it becomes very easy to understand what are the coordinate transformations that correspond to these Haney-Witten transitions. And once you do that, you can perform one of these that bring you to one of these generalized toric polygons, and see that what's going on is that at the level of the space-time coordinates of this geometry, it looks as the mirror of a toric Calabi-Yau, but there seems to be some constraints for your complex structure moduli, and then we argue that when you go back, what this corresponds to is some constraints for your Kähler moduli, in particular preventing you from resolving some singularity. Now, it's also very interesting that the way these Haney-Witten transitions look in the mirror has been studied a lot in mathematical literature. It goes under the name of mutation of Laurent polynomials. And this allows us to also import some machinery from that context and trying to understand some physical applications. And then the basic punchline of our thing is, well, as I just told you, the geometry of GTPs should be understood as some toric Calabi-Yau, but with frozen singularities. Exactly what's the mechanism for this freezing remains to be completely understood. It seems that all the ingredients are there for the 3-form of M-theory to play a role. Once we start exploring the mutation literature, one of the very first things that we see is that they give us this period, and the mathematicians tell us that if 2 periods are equal, then the 2 geometries are related by a sequence of these mutations. And this is extremely useful because then it allows me to, I give you 2 completely different brainwebs, and you can say if these are or aren't related by a sequence of Haney-Witten moves. And lastly, you can also
thank you very much.
Thank you.
Okay, questions?
Questions? 3, 2, 1. Next speaker!
Thanks.